Thank you for all being there this afternoon. Today I'm presenting my bachelor thesis presentation for the Faculty of Computer Science, and I'm going to talk about adaptive modeling for the development of schizophrenia, and therefore I'll focus on epigenetics and false memory generation. So first off, I'll talk about a little bit of the background of schizophrenia and epigenetics. Then next up, I'll talk about the adaptive model I created and also the simulation experiments based on these adaptive model. And then I'll end with a conclusion and talk about some future research, which is very interesting for my model. But first, some background information about schizophrenia and epigenetics. So schizophrenia is a complex disease which can be categorized in three main symptoms. First off, positive symptoms, which contain hallucinations, but also contain delusions. Also negative symptoms, which are mostly depression-like symptoms, such as lack of motivation, but also lack of expression of emotions. And also cognitive symptoms. And cognitive symptoms are memory-related problems and also concentration problems. So it's mostly thought that schizophrenia is a genetic disorder, but this is not fully the case. It's also very much influenced by environmental factors. So for example, think about abuse of neglect, which can also lead to an epigenetic effect, and in turn to you developing schizophrenia. And that is really what my thesis is about. So I focused on the effect of neglect and developing schizophrenia, and then a focus on the symptoms of false memory generation. But first off, I first want to talk about how these symptoms as false memory generation in schizophrenia come up. So as you can see here is the hippocampus, and the hippocampus is divided into three regions. We have the CA1 region, the CA3, and the DG. My research is mostly on the CA3 region. So this CA3 region has a lot of pyramidal neurons, and these pyramidal neurons have dendrites on it. And these dendrites have NMDA receptors on it. And what's interesting about the NMDA receptors is that it can have subunits on it. And this subunit can be GLUN2B or GLUN2A, depending on your age. Because when you're under 18, you mostly have immature neurons. And immature neurons have GLUN2B on it. Mature neurons, when you're over 18, have GLUN2A on it. And what's the big difference about this? The big difference is that GLUN2B is on neurons with a very high plasticity. So the neurons are very active when they have GLUN2B. So you can imagine when you're young, you have a lot of high active neurons. But when you get older and you get a more mature version of GLUN2B, namely GLUN2A, the synaptic plasticity of these neurons will be much lower. So eventually you'll have much lower plasticity neurons. So how do we get GLUN2B? If GLUN2B gets expressed, and because this stores the information of GLUN2B, you get GLUN2B. And GLUN2A stores the information for GLUN2A. But there's something interesting about GLUN2B, because we have something that is controlling this gene, and this is the RE1 silencing transcription factor, also known as REST. And REST, it's in the name, silences GLUN2B. And when does this happen? It happens when you mature. When you mature, what I already told, you get much more GLUN2A subunits compared to GLUN2B because they mature. And this is done because of this REST. REST blocks GLUN2B, and in turn, there will be less GLUN2B. So this is usually what happens when you get older. But it can also go differently. For example, when you have an unhealthy upbringing and you experience, for example, neglect or abuse. What then happens, for example, with this boy, it can happen that REST stops silencing GLUN2B because you feel a lot of emotion during this phase, and it leads to an epigenetic effect where REST stops blocking GLUN2B. And in turn, what you get is a lot more GLUN2B because GLUN2B's expression stops. So then you have a lot of more immature neurons with a very high synaptic plasticity. And this in turn leads to a hyperactivity in the hippocampus. And when there is a high activity in the hippocampus, these false memory generations come up increasingly, because a lot of immature neurons have this high synaptic plasticity. So this is where I'm going to talk about today. I'm going to talk first off about a typical postnatal development, and I did some simulation experiments for this. So this is somebody without an unhealthy upbringing and who is not experiencing neglect. And the second simulation I'm doing is about an atypical postnatal development. So somebody who gets neglect during a phase in his life and eventually develops schizophrenia symptoms as false memory generation because of that. But first off, I want to talk about the functions I used. I used the advanced logistic sum, and I used the step 1 function. So here you got the notation of them, and here's the formula. So what the advanced logistic sum does is it combines multiple inputs into a single output because it takes the average of it. And it also has 2 parameters. It has the steepness and the threshold. The steepness decides how powerful the effect is. So if it's more steep, it will be a more powerful effect. And if it's less steep, it has a less impactful effect. And I use this to manipulate the results of my simulation. Moreover, we have the threshold, who decides when is this turning point, or for example, not a steep line to a more steeper line. Think about, for example, experiencing pain. When you have a high threshold of pain, it will be more difficult to feel this pain. So it will be first very not steep and then turn into steep. While if you have a low threshold pain, it will very quickly, you'll feel the pain. So that's the advanced logistic sum, but I also use the step 1 function. And I use the step 1 function to simulate the experience of neglect. Because what the step 1 function does, it works binary. It's like a flashlight. For example, it can be 0 or 1. So you turn it on, and then for a period of time, you can turn it off. So for example, if you think about neglect, we have a start time, for example, 5 years, and an end time, 12 years. And that is the period of neglect what I used. But let's first dive a little bit more into the adaptive model that I made. So first off, here we have the base level layer for memory generation. And this level is focused on generating true or false memories and experiencing the neglect and trauma. Then we have the first self model, which is focused on the brain structure. And this is really about the synaptic plasticity of the neurons. The second level is the enzyme level, which produce GLUN2B, where I focused on my study. And in order for these enzymes to make GLUN2B, we need information. We need the information which is stored in GRIN2B. So that is gotten from the fourth level, and the third level has the messenger RNA that transports this information from GRIN2B to the enzyme level in order to make GLUN2B. And lastly, I have the epigenetic level for REST. That is the transcription factor that controls GRIN2B. But let's dive a little bit more into the base level. I hope you can see that I zoom in. I think so. So I first have here the neglect, the con for neglect state. And this state tells that somebody is experiencing neglect, the context for neglect. And because of this, you feel and experience the trauma from it. So I have the sensory state for trauma. And after that, you'll represent the trauma in your head. And that is why I have the sensory representation state for trauma. So next up, you have to think about it. When you experience so much trauma and stress from the neglect, you will have a lot of emotion during that phase. And there's where the emotion regulation comes in. So here up, I have the preparation state for a feeling B and the feeling state for a feeling B. We have the prefrontal cortex, which controls the feeling. So this is really the emotion regulation process. So you have to imagine when you feel a lot during this phase, because of the trauma, it will give a very big impact on your feeling state. And this is where the epigenetic effect comes in. And that's why I have here the blue lines, which go up completely to the top layer which is the epigenetic layer. And here, the malfunctioning of REST starts to happen. And REST starts to stop silencing the green2B gene. So that is where this pink arrow comes down. Green2B starts to being expressed again because it's not silenced anymore by the top layer. And the messenger RNA is going to transport the information of green2B to the enzyme level. And when the enzymes start producing gluN2B, gluN2B will increase. And when gluN2B increases, the plasticity effect of gluN2A and gluN2B will increase. Because what I already told, gluN2B has a very high plasticity. So after that, the connections of the neurons, of the pyramidal neurons, will very much increase. And in turn, the hippocampus will also get a very active, very high activity. So because of this, the false memory generation here will more likely be happening than the true memory generation here. So think about, for example, I'm going to lunch with my friends, and after that she tells me about the situation. And I represent that situation, and I'll think about a memory about it. It will be more likely that I generate a false memory than a true memory because of this epigenetic effect. So this is it for the multi-level adaptive layer. And I'll focus right now more on the simulation experiments that I did. And this is for the typical postnatal development. So a person who is not experiencing neglect and in turn doesn't develop schizophrenia. So in the left, I have the base level layer, which is this pink layer over here. And on the right, I have all the adaptive layers, which are all these layers. So we have on the x-axis, we have the time. And the time, I made it that every hundredth on the x-axis is 5 years. So in total, this will be 25 years of a person's life. But first, I want to zoom in into the base layer. So first off, what we see is that the context for neglect is not there because somebody is not experiencing neglect. Also, because the neglect is not there, the sensory states for trauma will also not be there, because if there's no neglect, there will also be no trauma. What I did is I put the trauma state, or sorry, not trauma, but the true memory state much higher than the false memory state. This is because in the first place, it's more likely that you generate a true memory than a false memory. But then something interesting happens, which is normal. The false memory state comes up together with a hippocampus state, indicating that the activity of the hippocampus is starting to rise, together with the false memory generation. Why is this? So this is completely normal, because when you're young, as I already told, you have a lot of immature neurons which contain gluN2B, as you can see here. So there is a lot more gluN2B than gluN2A. So the subunit plasticity effect is also higher. But what is going to happen is very interesting, because here we have the W states, which are responsible for producing the gluN2B protein, and also for the expression of green2B, who is responsible for gluN2B protein. Oh, so what happens is it's starting to decrease, which means that more gluN2B is being matured to gluN2A. So what you see happening here is that gluN2B is starting to decrease, while gluN2A is starting to increase, which shows the maturation process of this subunit. What is more interesting is that the subunit plasticity effect is starting to decrease. And here you see when a person becomes older, you get more mature neurons with a lower level of plasticity. So in turn, what we see, first the hippocampus was very active, but then it became less active because of this increase in gluN2A instead of gluN2B. And what we see with the false memory generation is that it also goes down completely to zero, because now with these mature neurons, the hippocampus will be less active and do it very well with the generation process. So we also see that here the true memory will be stable. So we will generate a lot more true memories. So what happens when there's an atypical postnatal development? So somebody is experiencing neglect. So focus first on the base layer again. We see that here from 100 to 250, which is the time from 5 to 12 years old, there's neglect. Before that, there is no neglect. So the same pattern happens as in the typical postnatal development. So what we see, the false memory is starting to rise, while the true memory stays stable. Hippocampal activity is also rising. And here, in adaptive layer, again, the W states start to decrease, showing that they are ready to go from GLUN2 B to GLUN2 A. But then neglect happens. A period of very much trauma, so that's why the sensory state for trauma and the sensory representation state for trauma, as you can see here, come up. But not only that, the preparation state for the feeling B and the feeling state for the feeling B, together with the prefrontal cortex who controls these two variables, also come up because you feel a lot of high emotion during this phase. So what happens then? Even though the hippocampal activity was starting to decrease together with a false memory generation, you feel a lot of these emotions, which leads that rest is starting to malfunction. And that is seen by these W states who are increasing. These W states increase, and because of this malfunctioning of rest, so the GRIN2B gene is not being silenced anymore. So this W states increase shows that the GRIN2B expression is increasing, and also the protein GLUN2B is starting to increase as well. So what happens then is interesting, because GLUN2B was decreasing, but now it starts to increase again, showing that a lot more immature neurons are there. And what we see in GLUN2A is it gets a stable level. And this is because GLUN2B is increasing, and therefore GLUN2B is not maturing anymore to GLUN2A. So this level stays stable. And what we also see is the subunit plasticity effect also comes up. But what the most interesting thing is that the hippocampal activity also comes up. Even though this period of neglect is over, the activity stays high because of these immature neurons. And also, we see that the true memory generation process is also increasing and reaching almost the same level as the true memory state, indicating that false memories are generated a lot more right now. So what can we conclude about this is that environmental factors are very important in the development of schizophrenia. And it can even lead to changes of the brain if you, for example, have a period of neglect or abuse. We can also conclude that the hippocampal activity is very much related to the false memory generation. And then if there are a lot of immature neurons, that hippocampal activity goes up and false memory gets generated as much as true memories. So what can we do as future research? It will be very interesting to focus more on the GRIN2A gene, since it's responsible for the GLUN2 producing the GLUN2A. Why is this interesting? Is because I think it has a lot to do with this research I did, but I couldn't find a lot of research about it. So it could be very much interesting that why also this expression of GRIN2A gets hindered, because I really couldn't find that in the literature research I did. What will be also interesting is to focus on different regions of the hippocampus, since I only focused on the CA3 region. But the CA1 region also has pyramidal neurons, which are also very much responsible for memory generation. So this will be an interesting field to look into as well. And lastly, what will be also very interesting is to look into diagnostic approaches of these false memories. I read an article about hippocampal activity, and that the frequency can define if somebody's experiencing these false memories generation or not. And this will be very interesting, because if you think about true and false memories, it's very hard to diagnose this with a person. So that will be a very much interesting research for my research. So that was it. Do you have questions?